Today's topic is Zener diode. The introduction, working principle, and characteristics of Zener diode are to be discussed. Zener diode introduction. Diode means two electrode device. Zener is a special type of PN junction diode. This Zener diode mainly works in the reverse biased condition. Our ordinary PN junction diode connected in reverse biased condition is not used as a Zener diode. This phenomenon is described by Clarence Zener. Hence, this PN junction diode is called Zener diode. The schematic of a Zener diode is shown in figure. It's a diode, two-terminal device. The left part is anode and the right part is cathode. Zener diode is a PN junction diode, but it's specially designed. The PN layers are highly doped. That is a special characteristic of the Zener diode. The Zener diode allows current in only one direction, that is in the reverse biased condition. The figure shows the first one is the appearance of the Zener diode. The second one is schematic. The green color arrow shows the direction of the current flow. Figure shows the Zener diode with biasing conditions. The PN layer of a Zener diode is connected with the battery. The N layer is connected to the positive terminal of the battery. P layer is connected to the negative terminal of the battery. The depletion layer is shown in the yellow color. The connection is a reverse biased connection. Below the circuit, the appearance and schematic symbol of the Zener diode. The current blue color arrow shows the direction of normal diode current flow. On the right side is the red color arrow mark shows the current flow in the Zener diode. Working principle of Zener diode. Zener diode is working in the reverse biased condition. Here, two types of breakdowns are there: Avalanche breakdown and Zener breakdown. First, we are going to see the Avalanche breakdown. When a PN junction diode is in the reverse biased condition, we know that the depletion layer becomes wider. That is, the majority carriers on either side of the PN layer are attracted by the battery terminals. The depletion layer width is increased as the voltage increased. And if the reverse bias voltage across the diode is increased continuously, the depletion layer becomes more and more wider. Once the depletion layer increases, there will be a certain minimum minority carrier movements across the junction. That minority carrier movement is the reverse saturation current. After certain reverse voltage across the junction, the minority carriers get sufficient kinetic energy due to the strong electric field free electrons with sufficient kinetic energy collide with the immovable ions in the depletion layer. So that free electrons knock out more number of free electrons when collide with the immovable ions. When more number of free electrons are there in the PN layer, that free electrons get sufficient kinetic energy from the same electric field. That free electrons again create the more number of free electrons by collision. This cumulative phenomenon very soon create huge number of free electrons in the depletion layer. At this point, the entire diode will become conductive. That is, when more number of electrons are there is a free movement of electrons, then current flow takes place. This type of breakdown of the depletion layer is known as avalanche breakdown. But this breakdown is not quite sharp. The figure shows the Zener diode with reverse biased condition. P-type negative terminal, N-type to the positive terminal. The depletion layer increases. In the depletion layer, we are having the immovable ions. When the external voltage increases, some minority carriers from N to P and P to N collide with the immovable ions. That immovable ions are, due to the collision, the free electrons are created. The process is continuous. Then more number of free electrons are created due to the collision. Next, we are going to see the Zener breakdown. Zener breakdown is similar to the avalanche breakdown. That is, when a PN junction diode is connected in a reverse biased condition. Here, the PN junction are highly doped. The higher concentration of impurity atoms causes higher concentration of ions in the depletion layer. That is, when PN layer is formed, the doping concentrations are very high. So once the doping concentrations are high, the immovable ions in the depletion layer also high. When this type of semiconductor PN junction diode is reverse biased, once the reverse bias condition, the depletion layer increases, whereas here highly doped condition, the width of the depletion layer becomes thinner than that in a normally doped diode. So that is the main difference between ordinary diode and Zener diode. Usually reverse biased condition, the depletion layer increases, whereas in Zener diode, the PN junction diode, that is, the PN layers are highly doped. The width of the depletion layer is very thin. Due to this thinner depletion layer, voltage gradient or electric field across the depletion layer is quite high. Figure shows the highly doped PN layer with reverse biased condition. If the reverse voltage is continued to increase after a certain applied voltage, the electrons from the covalent bonds within the depletion region come out. So these covalent bond electrons make the depletion layer more conductive. This breakdown is called Zener breakdown. The voltage at which this breakdown occurs is called Zener voltage. Now we are going to see the comparison between avalanche and Zener breakdown. Zener breakdown occurs at a lower voltage level. Then the avalanche breakdown takes place. The Zener breakdown is much sharper than the avalanche breakdown. When a Zener diode is connected across a voltage source, the source voltage is greater than the Zener voltage. The voltage across the diode remains fixed, constant, irrespective of the source voltage. That is a special characteristic of the Zener diode. Although at that condition, current through the diode can be of any value depending on the load connected with the diode. That is why we use a Zener diode mainly for controlling voltage in different circuits. Characteristics of a Zener diode. It consists of two parts of the characteristics. Similar to our PN junction diode, here also forward bias characteristics and reverse bias characteristics. The forward bias characteristics of a Zener diode is similar to that of a PN junction diode. That is, forward characteristics is a graph between forward voltage and forward current. The device is either silicon or germanium. 0.3 to 0.7 volt, that is 0 to 0.3 or 0 to 0.7, the current is very minimum. Once it crosses the 0.3 or 0.7, the current increases exponentially, then linearly. In the reverse bias condition, that is the reverse characteristics, a curve between reverse current and the reverse voltage, that is VR versus IR. In the reverse bias, as the source voltage increases, the current is due to the minority carriers, very minimum current flows through the device. Once the source voltage increases near to the VZ point in the graph, that breakdown takes place, Zener breakdown takes place. That is, the minority carrier, that is covalent bonds, more number of electrons will be come out. That breakdown takes place. That breakdown is a sharper breakdown. That is the Zener breakdown. That another characteristics we are having in the reverse bias state, the Zener breakdown and avalanche breakdown. So avalanche breakdown is not sharper than the Zener breakdown. We can see the knee voltage in the another graph. The voltage VZ is the Zener voltage. At this point, the current increases rapidly. If the applied reverse voltage across the diode is greater than the Zener voltage, diode provides a conductive path to the current through it. Hence, there is no chance for further avalanche breakdown in it. For diodes that are lightly doped, the breakdown is dominated by the avalanche effect rather than the Zener effect. The application of the Zener diode is an voltage regulator. So far, we have discussed the introduction part of the Zener diode, working principle of Zener diode in that avalanche breakdown, Zener breakdown, and the characteristics of the Zener breakdown. The main difference between the Zener diode and a PN junction diode is the Zener diode works in the reverse bias direction, whereas our normal PN junction diode works in the forward bias characteristics. There is no reverse bias condition. That is the main difference.